Okay, so last time we discussed how the we started with the different layers of the database system, and we decided that we'll be starting with the storage manager, the lowest layer of the database system, and uh, then we talked about how different storages, like how we deal with disk-based systems, and we are going to recap what we did in the last video. So we discussed that how there are hierarchies to the storages. Like as you can see, like we have SSDs and HDDs and network storages below the in the bottom half of the stack, and DRAM, CPU caches, and registers in the above part of the stack. So as you go above the stack, like as you go up the stack, the storages become fast, they become expensive, and they become smaller as well. But as you traverse down the stack, the storages they become slow and but they are larger and cheaper. So in contrast, like if you want to compare, buying a CPU with a lot of registers is much expensive than buying a SSD with, let's say, 512 gigabytes of space. So yeah, that's what we did last time, and we also do this line where uh, everything starting from DRAM and above is volatile. That is, you turn off the machine and the data goes away. And anything below that is volatile. So you turn off the power and it persists your data. So we also compared access times that accessing data from caches is super fast, and to take a human reference of it, we converted these nanoseconds to seconds. So this gave us some idea of how expensive it is to fetch data from each of the memory storages. Then we also discussed that disks love sequential access, that if you go about accessing blocks sequentially, it will be much faster as to when you randomly ask for blocks from around the disk. So like if I'm reading block 1, 2, 3, 4 sequentially, that will be much faster if I'm reading block 1, then I'm reading 9, and then I'm reading 23, and so on. So these are just arbitrary numbers which I just they just popped into my head. Then we discussed that what is a database? They are just files on disk, and uh, a disk-oriented database management system will just have a buffer pool which will stay in the main memory, and the pages from the disk will be fetched into that buffer pool. And what is buffer pool? It is nothing but a cache for our uh, database pages. So whatever is stored on the disk is brought into memory, and then operation is done on that, read or writes or any operations you want to do on that page. Then we saw how there's a page directory which tells us that what offset do I need to jump into the page file, like the database file, so that I can fetch page 2, page 3, page 4. And once I have that page in the buffer pool, I will just jump to that particular offset to read a tuple or to read a attribute of a tuple. And we also discussed that until the buffer pool, till the buffer pool, the system has no knowledge about the logical ordering of data. So there is no concept of tuples till buffer pool and data and the storage manager. They have no idea what tuples are. They are just reading and writing raw bytes in and out of the system. Uh, there's an execution engine which sits on top of that, which has some logical idea of yes, what I want to fetch, what I'm getting in return, like what serialized bytes I'm getting, and how do I convert those how do I deserialize those bytes into actual representable data. So yeah, then we saw that how pages are updated in the buffer pool as well, and yeah. So yeah, we finished on this slide that we are going to start with the file storage. So what are databases? As I'm already saying, databases are nothing but they are just files on disk. So they are just normal files on disk, but if you look at it with the naked eye, or you just open the file in the text editor, you wouldn't see much, because there will be bits and pieces that you might recognize. That yes, if I'm storing a column name, then you might see different names in the file, but you cannot make sense out of that what tuple it belongs to. So what database does for us is, the databases are specialized softwares which writes these particular files and then reads them back efficiently, so that we can just make sense out of the data stored in them. So database in my head is just a very large system with which deserializes and serializes data through and to the disk. So yeah, so let's talk about file formats now. We know that there are different type of system, like Oracle is there, Teradata is there, and then there is MySQL. Then we have Postgres, PG, and there are a lot of systems, like we have Oracle. Oracle we talked about, MS SQL, Microsoft SQL Server, and what do we have? We have a lot of systems. Each of these databases write their own files to disk. So as I said that databases are just files on disk, but any database management software you choose, they will have their own format of writing these files. So let's say MySQL wrote some files and stored some data in those files. If you try to read those files with the help of Postgres, Postgres will not be able to deserialize that. Why? Because that file format is proprietary to that particular database system. There are some open source file systems, like Andy talked about Parquet and Orc, and they are the file system which are kind of universal file systems, which some systems can implement so that you maintain portability of data across different systems. But usually, most of the mainstream systems, they don't use these general purpose file formats. They prefer to write their own. So MySQL files will be different from Postgres. Postgres files will be different from Microsoft Server, and those will be different from what Oracle writes to the disk. And yeah. So, yes, this slide was very interesting to me when I was looking at the lecture. So, Andy was telling in this that, as I talked before also, that when a database system writes to a file, it does not directly write it to the disk controller. Like it does not manipulate the disk controller. What it does is it uses the usual operating system syscalls, fread, fwrite, and fopen, uh, and the operating system does the writing part. So database system is just a usual software, user level software, which is running on the user space, and you just make system calls to read and write files. But uh, Oracle did something different back in when they bought Sun Microsystems. What they did was they bought Sun Microsystems, so they got their hands on the Sun Micros. They have an operating system, I guess. So what they started was they started embedding these system calls in the operating system as well. So that whenever your database, their database, the Oracle database, when it makes a write call or a read call uh, through the operating system does not go through the usual measures. It knows that it is the thing is being called by a Oracle database, and then you can just speed up things. But then this was not scalable, as I think I'm not very sure, but this was not scalable because the hardware manufacturer, the CPU, the Intel put out their new instruction set. So it was not the Oracle was not able to match the pace. So they were able to put their instruction in the operating system, like system calls, special system call for the data Oracle database. But x86, like Intel put out another instruction set, and they were not able to match the pace. So I don't really think that I made sense in the past 2 minutes. But this was something that Oracle did, that they bypassed the usual operating system and the file system, and they embedded their own thing in the files in the operating system, like not going through the usual measures of the file system, like writing using the normal file system, but they embedded some instructions so that Oracle, like their database, could be faster. But I think that this died out soon, and yeah. So let's talk about storage manager. Uh, so what is a storage manager? We talked about this before, that uh, it is just that layer of database management system which reads and writes pages in and out of the database file. So your database can have, hold on, huh. Your database can have a single file, can be stored in a single file, the whole of the database. MySQL, DuckDB do it, or you can have multiple directories and multiple files. Like you can have one file for each table, one file for each index, one file for each filter. You can do various things in your system depending on how you design the system. And yeah, so what Storage Manager does is when you plug in a Storage Manager, it knows that what file format you're using, what kind of database directory hierarchy you're using, if you're using multi-directory hierarchy for a database, or you're storing the whole database in a single file. So reading and writing to those files is the job of the storage manager. So we're going to read through this. Uh, so storage manager, they also do their own scheduling. This is storage managers kind of trying to be smart, that uh, the upper layers of the system can give us writes, but it is on us that how do we efficiently order those right so that we can maximize their sequential write or read. So what that will do is in modern systems it will increase our throughput, and in modern necessities I don't think that is a problem though. But uh, I was discussing this the day before with a friend that uh, back in the day when we had the HDDs, we had the problem of that random reads and writes because the head had to move from the spindle. But we don't have this problem in SSDs. But he gave me a very logical argument though. Forgot the argument though. Hold on, we can figure it out. Yes. So I asked. Wait, I messed up. Yes. So asked ChatGPT about it, and he also gave me a logical argument. Although I forgot what my friend told me, I'll have to ask him again. But ChatGPT gave me this answer that yes, and it makes sense that if you're doing random writes, you will try to fill out the blocks randomly. So you might have internal fragmentation or external fragmentation, and when your blocks get fragmented and then you try to uh, rewrite blocks with updated data, that just wears out the SSD. So like each block has some lifetime, had some number of writes that it can tolerate, and after that the block wears out. So if you do random writes, you might end up fragmenting your disk hard, and If you do sequential writes, it will allow the disk to compact your data in such a way that you can use minimal blocks for it. So yeah, that makes sense, but yeah, I'll get back to it though. So yeah, so the storage managers just schedule their own reads and writes, that how they want to read from the disk and what is the most efficient way to read from it, just to improve spatial and temporal locality. So we talked about spatial and temporal locality in the last video as well. That spatial locality is when you have two pieces of data which are located to close to one another and are and tend to be used together, like in one after the other. So we can think of an array. So let's say we have an array, and this is the indexes. So let's say I start a loop, and my instruction goes to the CPU. The CPU tells the DMA, not the DMA, sorry, the MMU to fetch this zeroth position. So what my MMU will do, it will fetch the zeroth position, but uh, given that the modern CPUs are highly optimized, they will also try to cache the other locations. Like they will fetch 1, 2, and 3 for me. So that will make my loop very quick because now all my indexes will be cached in the L3, L2, or L1 cache somewhere. But this is called as spatial locality. That data that lies close to each other is tends to be used together. And another one is temporal locality. That data once used is uh, has the probability of being used again. So yeah, that I think I got confused last time also in this, but yeah, that's what it is about. That piece of data is which is used once is cached, and then it is probable that it would be used again. Like think of the I variable in a for loop, which is just which is kept on which keeps on incrementing each time I run through a loop. And yeah, that would be an example of temporal locality. Okay, so what Story Manager also does is, as we talked about the pages, that you track the pages in the database file, and there is a statement down below that a database typically does not maintain multiple copies of a page on disk. Now, this might be a bit. I'm not saying I'm an expert on databases, but I'm just saying that I did see an example where there was a page. So let's say, I think it was called, it is an example in this book. Wait, I'm not able to find it though. But I read somewhere that let's say we are updating a page, right? You're updating a page, and what you do is you bring it in the buffer pool, you change it, and till the time you are changing it, you maintain a copy on the disk or in the buffer pool so that you don't block readers through it. Because till you have committed, till a transaction has committed, you are still holding a latch, like a lock to that page, and you might also block other readers. So till you have not committed, you can maintain a copy of the page in the buffer pool or in the disk, and when you commit, you write the new page, uh, and you just switch the pointers. Like let's say it's a B tree, and I might not be making sense right now if you're new to databases, but if let's say you have a B tree, and I'm just making two levels, and this is my parent and this is my child. So let's say I'm updating this particular page I'm updating. So what I'll do is I'll bring this to the buffer pool, and I'll start updating this. But till that time, till I have committed, I can maintain this page in on the disk or in the buffer pool, and my readers can just read usually till I have committed. I don't need to hold the locks, depending on what isolation levels I'm running at though. But you could do this, that you maintain this another copy in the system. So that is why I think this typically word is there that typically does not maintain a multiple copies of pages on disk. But I'm just saying you could do this, and there's a use case for it. And also, I think I read it somewhere. It's some kind of B tree. Uh, it's in the chapter of immutability. Yes, which chapter is it? It is somewhere. I'll have to find it to take out time. Okay. Anyways, let's talk about pages now. So what is a page? It's nothing but a small segment of the database file. And pages are usually fixed size, and usually the whole database system, the open source ones, as far as I know, they use fixed size pages. Like if you just define a page size, it will be used for the whole system, or for a particular database. But in enterprise systems like Oracle and MS SQL Server, you can do is you can define page sizes per table, per database, or per index. You can just there are so many different modifications you can make in enterprise systems. I guess that's what the money is for. But in usually in the open source system, there is no such you usually define a page size for your database, and the whole system operates on that page size. So what is a page? Page is just a part of a database file on the disk. It can. I'm not saying that what it stores. It might store table data. It might store indexes. It might store filters. It might store hash tables. It might store other data structures. It might store a skip list. I'm not saying anything. But a page is nothing but a storage location on a database file which the storage manager knows how to read. And pages are on disk, and when you bring them into the buffer pool, you put them in frames. So the good analogy I think like in my head I keep is you usually have photo frames, right? So what you have in memory are multiple photo frames, but there are no photos in that. So what are the photos? The photos are the pages on disk. So you bring you bring the pages and you put them in the frames on the buffer pool. So that's your caching of disk data. Okay, so as I said, like the first line reads, it can contain multiple tuples. Most systems do not mix page types. And some systems require page to be self-contained. Okay, what does this mean? Some systems require a page to be self-contained. What it means is that uh, some systems, what they'll do is everything you need to everything you need to interpret what's in the page is contained in the page. So let's say I have a table and it has two columns, name and email. So let's say I don't have the page directory. Let's say I don't have the metadata that this is a varchar, and this is an integer or what it is. I don't store separate metadata. What I do is I take that page, I write the header, and I store the metadata in the page itself. So whenever my storage manager comes along, I read the page out and whatever my execution engine needs to interpret that page will be contained in the page itself. So what it saves me is that I have a lot of granularity. Like if I lose some of the data, let's say I lose half of the data, I still can recover half of the data because I have the data to interpret that particular page is in the page itself. So this might be useful in disaster recovery and yeah, so I think what Postgres does is it does not use this. Usually, Postgres has this metadata table separately, and they store all the metadata there. And I think they also maintain a copy of that metadata just in case the first one gets corrupted. And first, you read in the metadata, and then you interpret what's in the pages itself. On Oracle, I think you can do that. This you can self-contain the page itself. I'm not very sure though. Okay, so each page is given a unique identifier. So what identifier is that? Each page has a file name. Okay, what file it is contained in, and it has a page number. So what I can do is, let's say I have a file name, uh, page number, and page size. So as I said, page size is usually universal. So all I need is these three parameters to locate a page. Once I get the file, the database file, I have the file. Now I get the page number. Let's say I need the page 20. So I get the page number 20. Okay. After that, I look at what is the page size. So each page, let's say it's 4 kilobytes. So let's say each page is 4 kilobytes. So I just multiply that number. 4 kilobytes into 20. That will give me an offset in the database file from where I just need to read 4 kilobytes. So once I read those 4 kilobytes, I'll have the page number 20. My math might be off here. Wait, no, I think it is correct. But if you multiply 20 into the 4 kilobytes, you'll get some byte offset. Like you convert this, right? This is 4 kilobytes, 96 bytes into 20. That will give you some number. And given that a file is just a long array of bytes, you jump to that particular offset and you read out the page. So, the next line says a page ID could be unique per database instance, per database, or per table. As I said, like file names will change, page number will change, and page sizes might change. In enterprise system, page sizes, you can define page sizes per database instance, per database, or per table. But that is usually not the case in open source ones. And a database uses an indirection layer to map IDs to page locations, to map IDs to physical location. That indirection layer is that computation I told you before. Not exactly though, but it might be. It might look something like this. That you are just you have a logical sense of what page number do I want to get to, and then you tell the storage manager that I need to get to this I need to get to this page number and in this particular database file, and you figure it out how do I want to get to it. And then the storage manager can do all things of like type of things as I said, like it can reorder your reads and reorder your writes to its own liking to just maintain efficiency. Yeah, that's what pages are all about. So yeah, this is an example. This is a very good example. Like Andy does a great job at describing his slides. He put out some databases and their page sizes, default page sizes. So yeah, yes, he also talked about that there in computer science there are three notion of pages. So one is the operating system page, the hardware page. What is the hardware page now? If you might ask. This is a RAM. Now I'm saying that RAM is also divided into chunks, usually 4 kilobytes chunk. So anytime I write to the RAM, I'm not writing a byte. I'm writing a whole page. So what is a page? A page in the DRAM sense is a chunk of data uh, that is guaranteed to be written together. So like when I'm writing, I write a whole page. Mm, wait, let me also. Yeah, don't take my word for it though. Yes, these hardware pages, I don't think they are written together. I need to study more about them. But there are hardware pages which divide the RAM into chunks, and there are OS pages. Now, what are OS pages? They are just the concepts of virtual memory, uh, which translate your logical addresses into physical addresses to the RAM. So what you have is you have something known as a TLB, translation local site buffer, and usually these pages are cached into that. And whenever your program asks to jump from some offset to some offset in your program, like to some instruction, that instruction is not physically mapped. Like if I'm asking that I want to jump to 0x88, this instruction. I'm not jumping directly to the physical memory of 0x88. What I'm doing is I am saying that I want to jump to this. The MMU does its tricks and it translates this virtual address into a physical address to the RAM. So at the RAM, this address might be translated to something arbitrary. It might be lying in the lower part of the RAM, in the upper part of the RAM, it's anywhere in the RAM. So what MMUs does is it translates this virtual address into a physical address, and the whole data storage portion where this mapping is stored is are known as OS pages. So that's another notion of a page, and then we have the database pages as we talked about. So yeah, here and we also talked about a hardware page is the largest block of data that a storage device can guarantee fail-safe writes. So I think yes, that's what yes that whenever you are doing a write, the RAM can guarantee that 4 kilobytes will be written or not written in its entirety. So it's the all or nothing. So default. Okay, so let's look at different database systems. SQLite. Okay, these all systems. Okay, let's talk about Oracle. You can have multiple, you can define your own page sizes because it's an enterprise system. In Microsoft SQL Server also you can define, but these are default page sizes you get if you install them. SQLite is a system that is an in-process system that it does not have a separate server for it. So you just import its library and it runs within your system, like within your application. It's a very light system, hence SQLite. And another interesting part of that is that it uses one database file for every database that you create in the system. So, like, let's say I have a students database, and then I have another database called as let's say food items. All those will be stored in one SQLite file, and that SQLite file is portable. It's like you can pick that file up and you can run it on some other system, and it will just work just as fine. Uh, I think they use a virtual machine for it. They convert your SQL instructions into uh, your virtual machine instructions, and then that virtual machine just interprets that and like reads to the local hardware. I think that is an interesting part that you convert that it's a JVM concept, so it's a good system. Then we have DB2, IBM DB2. I haven't heard about this. Like I did not hear about this before this listening to Andy. And apparently it's a big system. Like all the old banks and enterprise system use this. And yeah, there is something known as a RocksDB. RocksDB is out of Facebook. And I think what Andy told was that Google put out LevelDB first, and then Facebook forked it, and then they created RocksDB. It is an LSM store. What is an LSM store? It's a log structure merge tree store, but uh, let's not get to that. We have like there is a whole lecture dedicated towards that. Uh, then we have Ingress. Ingress is the prior version to Postgres. Then we have Postgres. Then we have Informix. I don't know what Informix is. Then we have MySQL, and it's the only database that has a default page size of 16K kilobytes. Well, uh, in the last video also I discussed that if you have a write-heavy workload, you might want to keep your pages small. You might want to keep your pages like of 4 kilobytes or 8 kilobytes, because then you are writing small chunks out to disk. Instead of if I have a read heavy workload, then I might want to have 1 megabyte of pages, because then I can read in more data to the buffer pool and get more data out of one page. But instead, if my workload is write heavy and I'm doing large pages, then let's say I want to update 10 bytes in a page, then I need to read that whole 1 megabyte of block, write those 10 bytes, and then write that 1 megabyte block back out. That's pretty wasteful, right? So yeah, that's what it is there. Uh, Optimal database. Okay, let's talk about this moment. So this slide tells what I just said, that if you have a read heavy workload, you might want to have larger page sizes. Fetching in single page brings in many tuples and are needed for the query. And write heavy, you just want smaller page sizes. The system might must write entire page to disk, even if only a small portion is modified. That's the same thing, right? If you want to update 10 bytes, then you have to write out the whole page. Okay, so now let's talk about the page storage architecture. So what is the page storage architecture? In layman terms, what page storage architecture says that how you're storing, we talked about pages, right? These are just chunks of the database file. But how you're storing those chunks also impacts your database system. Either you are, what I can do is I can create a database file and allocate, let's say, 1 gigabyte of this whole file, and then I can divide it into chunks, like 4 kilobytes chunk. Let's, we're just assuming that we are just dividing this file into 4 kilobytes chunk. So once we have divided this, now once let's say I have an insert that wants to bulk insert data. So while bulk inserting data, I could use this page. Once I've used this page, I could take a decision. Like if I was a dumbass and I was building a system for kids, then I would, let's say I've written to this and I want to create some mess. So what I'll do is I'll skip these blocks for no reason, and then I'll write it to the block at 500 megabyte offset. That's a random write. And once you, let's assume that our database is being hit with millions of queries a minute. Once you do this and you start reading data back in and out very frequently, this takes a hit. So how you organize your pages in the database file also is also an art, that it also has some advantages to how a database system works. So there are a couple of defined organizations. There is a heap file organization. What heap file organization is about is that you have no order to data. You're just writing data out sequentially as you can find places in pages. So let's say I have this, what I drew. So Postgres uses this. I have pages, and then when an insert comes in, I look at what page is free. Let's say this has some space, and I write data out somewhere here. And then once this page gets filled up, then another insert comes. I look at what other page is empty, and I write data to that. That is heap file organization. That you are just writing data without any order. You don't have order. Another thing is a tree file organization. So this is what Postgres does, heap file. And tree file organization is what by default MySQL does, or SQLite. And in the enterprise systems, I think you can switch between the two because, yeah, as I said, that's what the money is for. But what is a tree file organization? That when you're writing this disk, I mean this database file, one page, two page, three page. When an insert comes in, I will fill this, okay? But when another insert comes in, let's say I filled this page, I will not write to this page. Why? Because these pages have some logical ordering. It might not seem in the disk that these have some logical ordering, but these do have some logical ordering. And what kind of logical ordering? We don't care. Like the storage manager doesn't care about the logical ordering. The logical ordering will be figured out in the upper part of the system. Like the execution engine will handle it. It will know how to read a B tree. It will know how to read a red black tree, or it will know how to read a skip list. So internally, what the execution engine is imagining is that this is the first page. Let's say we'll number this one. Wait, I'll change colors. This is my first page. This is my second page. I hope you can see. Yep. This is my third page. Okay, so instead of doing just finding a place and putting data in that, I have some ordering to this. Let's say this is my first, this is my second, and this is my third. So if some of you have used uh, binary trees, what a binary tree does is uh, this is my node. Let's say I have 10 on this, and when I go to the left, I store all the values that are less than 10 to the left of it. That's 9. And let's say we have another value of 21, which got to store to the right. So when I'm looking through a binary search tree, what I'll do is I cut the tree in half. Actually, what if I land on this node and I'm looking for 21, I know that I will not go to the left. Why? Because 21 is greater than 10. So I will always jump to the right. So what it does is it cuts my tree in the half. So this portion is just out of the search area. Like it is not in my domain anymore. Like with the search function I will write, it is not in the domain and I will not search that area. I will not search the left nodes. I will just go to the right. Like now this thing has some logical ordering to it. The same thing is with tree file organization. That once I have a key and I want to fill that key in the tree file organization, I will not randomly find a place and put it. I will look at what is the logical ordering of that key, and I might jump to page 3 or I might jump to page 2. So page 3 is here. So if I was jumping to page 3, I will fill that portion here, even if my page 2 is empty. I will fill that portion here. And what the advantages of this, what I'm getting is at some higher level, I am promising that I will maintain some logical ordering to these pages, that I will know how to traverse this and it might or might not uh, give you better efficiency in reads or writes. So yeah, we will talk about this once we reach there. But yeah, that's what it is about. So sequential file organization. Andy talked about this that this is a depreciated thing, and no one uses it anymore. So I have not researched about it though, but I did some research about hashing file organization. So hashing file organization is nothing but just you are maintaining a hash table on the disk. So let's say you have keys, you are inserting keys and their values, and what you do is you just hash those keys and it allocates you to some bucket and you store the key there. This scheme is heavily used in making indexes nowadays, but it is not as widely used in storing data. So these two, heap file and the tree file organizations, are the two which are prominently used by modern systems. So Postgres uses heap file organization and MySQL uses tree file organization and SQLite as well. And yeah, uh, yeah, let's go. So let's talk about the heap file. We'll stop with the heap file today. I need to be at work. Yes. So we'll stop with the heap file today and we'll get on with the tree file organization in the next lecture. And yeah, these are taking a lot of time though. But anyways, what is a heap file? A heap file is nothing but it is just a database file with pages, and whenever you want to insert, you just find a free slot and you put it there. So, as I said, that a heap file is an unordered collection. So you have no sense of order in that. So your key one might be lying here, but if you delete that and then you insert that key again, it might be lying on the end of the page. Like it might be lying to somewhere on the 1 MB offset on the file or in some other page. So, how do you find order in heap files? You maintain indexes. So, we'll talk about indexes differently, but you usually maintain some order in the heap files once you start maintaining indexes. That also adds overhead that when you move things around in the heap files, how do you update the indexes? And are the indexes, all the indexes pointing to the physical location? Because they are, if I have 100 indexes and I update one tuple, I'll have to go and about and update 100 indexes. But you can also have secondary indexes which can point to the primary index, which can point to the physical location. So like once you update the physical location, the primary index gets updated and the secondary indexes can stay as it is because they're just an indirection layer. I'm jumping ahead of myself, but yeah, let's see. Okay, so there are no order. It is an unordered collection stored in random orders. Uh, yeah, so it is a random order. There's no logical ordering in that, and you just maintain some other data structures to define some order to that, some order to the heap files, and need additional metadata to track location of files and free space availability. In Postgres, there is something known as a free space map. I think so. Free space map. Yes. Uh, I think .fsm it stores it as. I think so. I'm not very sure. But if you create a table and you go to the directory, uh, we can do a tutorial actually. But I'll have to spin up a Postgres node. But anyways, if you if you create a table, you will also see that there is a free space map that is available, a free space map file that is available in the directory itself. We'll do a demo next time, but this file is there and it maintains the free space that all of the pages have. So when you need to insert, you just look at the free space map and you figure out what page has space, and then you go about and insert in that page. But that is also additional overhead that you're maintaining these files. Also, you need to update these files once you start filling pages. Uh, yeah, and there is also a vacuum command which actually just we'll talk about it. We'll do a demo and we'll talk about free space maps and what files they are tracking. So yeah, that's what heap file is there, unordered and random order of tuples, and you just maintain external data structures to maintain this. So so let's talk about this. How do I get a page? I talk to the page directory first because page directory knows that what page sizes I'm following. And if I'm looking at a page, my database file might be divided into multiple files. So like we can see that we have 4 files here. So my page directory will tell us that if I want to look at page 23, we are fetching page 23, it will be located in file number 2. So page directory will tell me the file location, and then I have the page size and I have the page like the page directory will also tell me that this file starts with this particular page. So I can do some math and jump to the directly offset where I can find the page. Uh, yes. So let's talk about page directory itself. So page directory can be for the data. So page directory can contain data about tables, indexes, or filters. So we can see that this directory has data about where if I want to jump to table X, which file should I go to? If I want to go to index Y, which file do I want to? Now again, indexes and tables are just objects like higher level logical objects to the database. But eventually they are just bytes on disk. So what are bytes on disk stored as? Files. So everything in a database is a file. You want to create filters, you go to a file, you create a file. You want to create a table, you create a file. And you want to create an index, you create a file. How you create a file is an art. How do you maintain order to those files in art? That's what it is about. I'm getting a bit poetic, but again, who's watching? Uh, So the directory tells me that where I want to jump and which files are contained and how do you want what page. Page directory might also contain some other information that what page size this particular object is storing. Like in enterprise system, table X might have a page size of 4 kilobytes, while the index Y might have a page size of 1 megabytes. Like why would you do that? I don't know, but uh, you can do this. So let's read through this. One entry per database object. This is a database object, tables, indexes. Must make sure that the page directories are in sync with the data pages. Uh, let's say that something happens to this page, page 0, and I am allocating, maybe not. Let's say I have some good system, some enterprise system that allows me to change page size on the fly. That I have a bunch of data and I just want to change the page size for the fun of it. That my data is written to 4 kilobyte pages. Now I want to transfer it to 1 megabyte pages. Maybe I'm transferring my data to a OLAP system. I want to do analytic queries and I just want the page sizes to be larger. So once I do that, I'm converting my system to a OLAP system. I also want to tell the page directory that yes, this table now follows 1 megabyte pages. So it should be synced with the actual structure that the file follows. Or else I might be propagating wrong information to the system above. And what other data is stored? Amount of free space per page. That's the metadata. This Yeah, not the directory, but the database itself stores the free amount of data per page, list of free pages and empty pages, and the page type. Either it is data or a metadata page. What is interesting is these two. For the first two, we'll see a demo for Postgres, that how it stores a free space map. There's a special dedicated file for storing free space map. I think, okay, so this was heap file organization. We'll talk about tree file organization also. But in the next lecture, we'll start with the page header. So we saw that how a database organizes, like what is the heap file and like what are the different ways that you can organize pages. Now we'll look in those pages and we'll see that how you can organize tuples in that page, like how you can organize tuples in that pages in those pages and some other metadata like sorry in that header you can see that the page might have some information that as it like we discussed 20 minutes ago that a page might be self-contained, so this header might contain the metadata to interpret the page itself. So we'll look at this in the next lecture and yeah, uh, I'll see you next time.